Alright, so I think this is recording. Let's take a look at this rational root theorem that allows us to list the possible rational zeros for a function. Um, we want to look at the constant term and list its factors. And these will all be plus or minus. And 1, 2, 4, 8, and 16 are all factors. They all divide the 16. And I'm not focusing my attention on the negative sign. If this was positive 16, it'd be the same list of factors. The factors of my leading coefficient 1, well, that's just plus or minus 1. And the factors of our constant term are our possible numerators, and the factors of the leading coefficient are the possible denominators. Our list of possible rational, so it's not irrational. If square root of 2 is a 0, this list is not going to find it. It's a list of possible rational zeros. So we might have this list and none of them actually check out. So since the denominator is 1, we just have 1 divided by 1, 2 divided by 1, 4 divided by 1 with the plus or minus. So whenever that leading coefficient is 1, this list is just generated again. If we get something that was like a 1 and a 2, you take every number, divide it by the 1, that denominator, then every number divided by the next denominator to write your list, or to do it in some organized fashion. So it said state the possible rational root. Roots are another word for zeros. Okay, so here's one of my answers. Now, if this graph crosses the x-axis at a rational zero, it'll be in this list. And we can either do synthetic division on these numbers or plug them in. And with a lot of times with just one, I'll just look at it and do the arithmetic rather than going through the whole synthetic division process. But let me show you. If I were to check 1 using synthetic division, I look here and I see that I do not have an x to the 5th. So 6, 5, 4, I do not have an x to the 3rd, and I do not have an x. So you might want to just simply plug in 1, do the arithmetic, and see if you get 0. So I've got 6, 5, 4, 3, 2, 1, and my constant term. Got that kind of close. Now, if this is a 0, then I have found a root in the list. If it's not 0, then I know that 1 is not an x-intercept, and I just move on to the next number. So you can probably see that this was not going to be. Yeah. So since this is not 0, I'm really not interested in this positive 1 at all, so I just move on to the next number in the list. And I may as well try negative 1. So again, I'm not getting 0. So 1 and negative 1 are not zeros of this rational function. They are not roots. Let's check out 2. This one will probably work, but I'm not the best at estimating. I have to actually go through. And you don't necessarily have to do them in order. If you have a feeling that one of these other numbers are the intercept, definitely jump to it and find it. So here we go. We found it. Okay, that's what we're in search of. So we know that just like the previous homeworks, that we can now factor this expression on the left-hand side to be x minus 2. And now we have this 1x to the 5th, 2x to the 4th, 5x cubed, 10x squared, 4x plus 8, and that equals 0. Because we're trying to solve this equation to find all of the roots, all of the x-intercepts, the zeros of the function. So now, what's nice is that this same list applies here, or it could be smaller. There's going to be no new numbers in the list. So if I look at since I have a leading coefficient of 1, this new list for this one is going to either be this list or smaller. There's going to be no new numbers that are generated. So the factors of 8 are 1, 2, 4, and 8. And of course they're positive and negative. So we did lose the 16 that we don't have to check. All right, I'm going to take this to another slide. All right. So if I were checking 1, I would just add the coefficients. You can see since all of these are positive, how would the number 1 ever add up to 0? So I'm not even going to bother trying to check 1 or any of these positive numbers. I know when I look at this to check negative values. So let's jump in, and we already had tried 1 and negative 1 and it didn't work. So let's try negative 2. We could try 2 again, but well, we just said not to try positive. Let's try negative 2. 5, 4, 3, 2, 1, 0. No greatest common factor. So we found one right off the bat. Sometimes you'll have to go. Sometimes unfortunately you try one and it's not until the last one that you try. Or like I say, it's possible you try every number in the list and there just aren't any rational zeros. There's either no, it doesn't cross the x-axis, or where it crosses the x-axis is like irrational numbers. Square root of 5 or square root of 2 or negative square root of 11, who knows what it could be. So we've got x minus 2, but now in factored form, this is x plus 2. And we're 1 degree less. This was 5, so now this is x to the 4th. We don't have an x cubed. And this is 5x squared plus 4. Now this is quadratic in form. We can actually factor this. We don't have to continue. Now, we could generate another list and use synthetic division again, but it's probably just easiest to recognize that that's quadratic in form, and that x squared times x squared gets us x to the 4th. 4 times 1 is 4, and 4 plus 1 is 5. And It wanted us to find all the rational roots. So it's not making us find irrational roots, and it's not making us find complex numbers. You know, um, when you expand to the set of complex numbers and you take the square root of -4, you might remember that that's 2i, and we actually do that as our last skill packet. So x squared plus 4 and x squared plus 1 will never be 0, because x squared can never be a -1 and x squared can never be a -4. So the only two rational solutions, the ones that can be written as a ratio, are 2 and negative. You can write 2 as 2 over 1, so they call that a rational number. So the only ones for this problem are 2 and -2. So that's what it wanted. It wanted us to generate the list, to use that list to factor the expression, and when in factored form, solve the equation and find the rational zeros. Alright, so I hope that helps.